Ladies and gentlemen, welcome back to another virtual laboratory, and in this lab experiment, we're going to be taking a look and putting more focus on MS, mass spectroscopy. So I know that you have watched those very abbreviated, short, not very many MS videos at all, and now you're ready to kind of start the MS laboratory experiment. But here's the thing, before you start this experiment, you're going to have to know a little bit about mass spec theory before you begin working on this. So you have to complete some of the preliminary lecture videos first on the coursework side of the house, and then pick up from that with the laboratory experiment. Otherwise, you won't know what you're doing, and then I'll get to sit back and laugh and go, ha 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 ha, I give you a 0. So please don't be that type of person. So in this laboratory experiment, we're going to be focused on a very similar activity to what we saw in infrared. So basically what this means is that I'm going to play the match game one more time, and I'm going to give you a series of different unknowns that you can choose from, and it's our job to match the names of those unknowns to the mass spectra that we have obtained from the piece of equipment together. All right, so the list of unknowns will be found in Blackboard. You'll be provided with those list of unknowns, and the very first thing that I would probably recommend to you is that once you get this list of unknowns, and the datasheet's probably going to ask for it too, you need to draw the structure of those unknowns, and you also probably need to go ahead and write down the formula weight for those unknowns, because folks, this is mass spec, and mass spec works by mass, and mass is formula weight, so you have to have it at some point in time. And the formula weight will be pretty important because, let's be honest here, with these particular kind of compounds, they all will have different formula weights, and this will be a very good key indicator of which mass spec goes with which compound. All right, so we are not only going to identify the M peak, which is the mass spec formula weight peak, but we're also going to identify the base peak as well, which is the most common fragment. And then we're going to introduce maybe one common fragment or two common fragments that show up in the spectra. And you will find that information on the data sheet when you make it to that point. All right. So match game, M peak, base peak, and a couple of other fragments, maybe one, possibly two fragments that are out there in the spectra that we will need to identify. And when I say identify, that means we are going to draw the structure that gives me the base peak, and we're going to draw the structure that gives me the fragment peak that we kind of want to know more information about. All right, so that overall is the goal of this laboratory experiment. So I'm assuming quite a bit of things here. I'm assuming, number one, that you have watched many, maybe not all, but many of the mass spec videos at this point. You know what M peaks are, you know what base peaks are, you know what fragmentation patterns are, you know that functional groups happen on molecules and functional groups will make the molecule split in a certain way. All of that information is needed in order to do well on this particular experiment. So if you've not watched those videos yet, you've got a lot of work to do. I don't, but you do. But my work comes when you start submitting all of it, and I have to grade all of it. So we kind of see the same story here. So with that said, I'm going to kind of turn it over to the PowerPoint presentation and let you kind of watch some videos of our mass spec system. So with this very first video, you're going to see kind of an overview of the gas chromatograph mass spectrometer. So the MS system is here to the right-hand side, and the mass spec system is to the left-hand side that's up underneath this AUTOSAMPLER carousel. So just a little brief intro about the machine before we go forward. All right, everyone, if you're hearing the hum, this is from our GC mass spec system. And what you're seeing here to the right-hand side of your computer screen is our gas chromatography system. We're not really going to focus on this part of the machine, and the reason is because this part of the machine is only doing separation and cleanup, and that's something that we've really not talked about so far in the mass spectroscopy lecture series. We're only focused on the MS. So I need you to understand that a lot of these compounds that are injected into the GCMS, which is actually coming from up here, those compounds are not 100% pure. So those impure compounds are getting injected into the GC, and you just saw one get injected, and now that compound plus all of the components that might be classified as impurities are circulating through the GC and getting separated. One by one, those compounds and impurities are getting fed over to the mass spec system, and the mass spec system is actually right here. That front door that you see there to the left, that front door actually opens up and it allows me to have access to the electron ionization chamber. So that's where all the magic is happening in the mass spectroscopy world. But this is something that I could show you, but the machine is running and it's got to stay under pressure, and I can't necessarily open that door up for you. But I could probably show you a picture or two in the PowerPoint presentation. What you see up here on the top is a carousel. This carousel is actually made to hold a number of different samples at one time, so that way we can just load all of these up and set it and forget it. So this carousel will actually hold over 100 samples for us, and we can just line them up, tell the software to inject them one by one. It will inject them, and that injection is taking place over here. This is what we call our injection needle or our injection port. So here you see probably a very faint image of a needle and a needle housing. That is what's sucking the sample up and injecting it into the GC mass spec system. So the sample is getting pulled from one of these little teeny bitty glass vials right there. I know it's out of focus, but there you go. That's where the samples are going to be housed. This arm grabs it like a grab machine, and it picks it up and it swings it over and it puts it into our sample compartment, which is going to be there. And then this will shift back and forth to line up with the needle. That needle injects the sample into the GC system, which is here. Inside the GC system, the sample goes round and 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 round. And then finally, that pure compound, as well as all the impurities, get sent over to the mass spec, which is right here. So in the mass spec, that's where the fragmentation is happening. That's where the compounds are breaking up into the fragments and the pieces and the parts. That's where the teeth are for the molecule. So in the mass spec, that's where the fragmentation is happening. That's where the compounds are breaking up into the fragments and the pieces and the parts. That's where the teeth are getting knocked out for the molecules. And then down the quadrupole it goes. So the quadrupole is actually lined up this way in the machine. So the compounds zoom down the tunnel, around the bend, and they hit the detector on the back end. So folks, that is our GCMS system that you're seeing here that we're using for this particular laboratory. So the mass spec is what we're going to focus on, not necessarily the GC part, which is here. All right, that's only doing separation. That's for a different course. That's for our chemical technology program. That is not necessarily for what we need to do today. All right. All right, so there's your intro to the machine. That's what the machine is doing for us, and we're going to be injecting these samples one by one, and we're going to have to wait and wait and wait and wait. But good news, this does it for me. I don't have to be over here with it for it to get finished. So in about an hour and a half, I'll come back, make sure that all of these samples were injected up at the top, and then just double check the chromatograms and make sure that they look good, as well as the mass spectra.
All right, folks, so you saw a little bit about our GC mass spec system. I will do a shameless plug for our program, which is the Chemical Technology program at Cape Fear Community College, a 2-year degree designed to provide you instrumentation training and laboratory training for any employer within the state of North Carolina or nationwide. So we're the only program in the state that actually does this type of training, and it focuses on pieces of equipment like this. So we do a little bit of basics, general chemistry, organic chemistry is typically required of the program. So you've already started the program, you just don't know. But we also focus more on the instrumentation pieces and parts and how they work and how to replace those and how to maintenance those and make sure that the data actually looks pretty good. So just a little bit about our GCMS system that we have in-house. So now in the next video, what I want to do is I want to focus on the AUTOSAMPLER tray. We kind of caught a little bit of the AUTOSAMPLER doing the job that it's supposed to do, but just in case you missed it and in case you wanted maybe a better view of it, this video is going to provide that for you. So this is just how the instrument is injecting the samples onto the GC system, which then in turn eventually get injected onto the mass spec system. And again, that's what we're focused on. We want MS here. So I'm not really going to go in deep on the GC part, but it's all about mass spec. All right, folks, so it's injecting a sample right now into the machine. So you see the grab arm that's lowering the sample down into the tray. Then that sample is going to go basically here where the needle's at. And the needle's going to clean itself, get rid of some waste. It kind of pre-rinses in the beginning. And then that injection needle is going to take up a sample portion and it will inject that sample portion down into the instrument. So really you're just kind of seeing the process of what happens here. We no longer manually inject anything by hand. It's now all done by instrumentation, which is kind of nice. That frees me up to do other things if I'm working in a laboratory. This method has a 0.3 microliter injection amount. And it's just made its injection. All right, so it will go through, it will clean itself, it will pre-rinse, and then it will get ready for the next injection that's in the lineup of all of the samples. And all of those samples right there have to be injected for this particular lab experiment. Okay, so I want to talk about something that I just briefly mentioned and didn't really elaborate on, and it said it was a 0.3 microliter injection, right? That sounds kind of crazy. 0.3 microliters. I want you to understand how tiny that is. So 1 milliliter, which is about 20 drops here. 20 drops of solution typically is about 1 milliliter, and 1 milliliter can be broken down into 1,000 parts. And if I take a milliliter and take 1 part of that 1,000 parts, that is 1 microliter. Very often in a biology class, a biotechnology course, or whatever the case is, they will introduce you to micropipetters. And a lot of times the micropipetters are 100 microliters to 1,000 microliters, meaning 0.1 mil to 1 milliliter. However, there are times that we need to go smaller. And we go smaller and we go into the vicinities of, 5 microliters, 10 microliters, maybe 1 microliter. But that is way too much stuff for this machine to do its job. So basically what that means is that we take a milliliter of solution, we bust it up into 1,000 equal parts, and one of those equal parts is a microliter. That is still way too big. I need 0.3 microliters to be injected. Folks, that's like a fraction of a drop. That's all that we need. The only thing that I'll say about the GC is that there's also a setting called split. And split, basically on the GC side of the house, looks at this 0.3 microliters and it says, you're too strong. That's way too much sample. Can you believe that? 1 milliliter's tiny enough, but 1 microliter is super, super tiny. And then we don't even use a full microliter. It's 0.3 microliters. And then that's even way too much. And we have to have a machine that does what we call split, which means split the sample into 2 portions, and 1 portion is out of the machine, and the other portion actually goes into the machine. I mean, sometimes this is like 1 out of 20 parts, or 1 out of 50 parts, or 1 out of 100 parts, meaning that if we had a split ratio of a 20, it would take that 0.3 microliters and it would break it up into 20 equal parts, and it would only inject 1 of those parts onto the machine, and the other 19 parts will leave. It never sees the mass spectrometer. So this gives you an idea of just simply the amount of sample that is required by the machines. It is fractions of a fraction of a drop. Super, super tiny, and a lot of people just don't really comprehend how little this actually needs in order to do its job pretty well. All right, so now what I want to show you is a little bit of the software screen. What's showing on my computer? What do I have to do as a user to go into an MS and kind of take a look at this screen and make sure that my settings are appropriate? So up here at the top, you will see 3 tabs. You'll see a sampler tab, a GC tab, and a mass spec tab. We're really only going to be focusing on the mass spec tab here, and that's what this video is going to be all about. All right, so stay tuned. Maybe take a look at your data sheet. You might find some information on that data sheet that's going to come from this video. Just hint, hint. So I want to show you a little bit more about the software. Here you're actually going to see an MS tab, and that MS of course is going to stand for the mass spectrometer. So I want to click this tab, and this will bring up some important information about the MS system for me as far as the method is concerned. First off, you see an on source temperature. This is the area that the electron beam is located, and as the compounds come through, they're going to basically break up, you're going to knock some teeth out, and then those fragments will go down the chamber. That has to be heated, and the reason that we heat that is to make sure that these compounds that I'm injecting on the inside will stay as a gas form and not condense to a liquid form. So right now this thing is set at 250 degrees as far as the on source temperature. The interface temperature, that is the piece that connects the gas chromatograph piece with the mass spectrometer piece. There is a tunnel that connects those 2 instruments together because they do different purposes, and we've talked about that very briefly. So that's also set at 250 just to make sure that these compounds stay as a vapor and not condense between leaving out of the GC and going into the MS for me. The solvent cut time is the next one. The solvent cut time you see at 0.75. So this is an idea that the solvent that maybe my sample is in, because it's not completely pure, we've put just a few drops of material into a solvent that's typically methanol or acetone or acetonitrile, and that solvent will take some time to come through the machine as well. We don't want to see the solvent because it overwhelms the detector, so we allow the detector to delay and not turn on immediately. And right now you're seeing that that delay is 0.75 minutes. So when the injection begins, it's going to not turn on the mass spectrometer until just a little under a minute. And then it will turn on the MS, and then we'll start to get data from that machine. Okay, down here you'll see a bottom table, and this bottom table will start at 1 minute, and it will go until the end of the analysis time, which is set at 26 minutes. If the peak comes off before 26 minutes, we'll cut it off. You'll never know the difference. However, what's also important here on this table is the start M to Z and the end M to Z. So I've got control of how I want the MS to report data and what I want it to watch for. So anything below formula weight of 35 and anything above formula weight of 250, it's going to ignore and it's not going to see it. And that's simply because I know what I'm injecting, I know what the minimum and maximums are. So instead of getting the MS to overwork itself, I've just narrowed it down so that way it only looks for those formula weight ranges and nothing more. So nothing less and nothing greater as far as M to Z goes. All right, so a little bit about the M to Z. The MS tab in the software. Nothing too complicated here, just a few settings that as a user I have to know something about.
All right, guys, so I want to explain that a little bit more, and I'll do that with a very quick diagram. So the way that our system is set up, our GC box is sitting over here to the right-hand side, and then this other box is sitting over to the left-hand side of that, and this is the GC system, and this is the MS system, which is really what we're mostly focused on here. So the reason that I'm drawing the diagram is because there were two temperatures in there that were very important, and one was the ion source and one was the interface. So the interface system, there's got to be an exit and an entry point. It's got to leave the GC and it's got to go into the mass spec. And I'm just going to draw that with this red bar right there. It's actually a kind of like a stainless steel tube that gets inserted in between the two pieces. And then there's a liner that goes on the inside of that. So that way all of my components and my samples are leaving the GC. They're going through this small little tunnel, and then that will take it over onto the mass spec side so the MS can do the job that it needs to do. That interface, that is what we call that. So this is the interface of the instrument, and that interface temperature is very important. So what happens is that if this is not hot enough, I could have a component that comes into the machine, and this component's going to travel through the GC and around and around and around and around and around and around through the column is what we call that, and then it'll eventually make its way over to the exit point of the GC. If this interface is not hot enough, then we run into the problem of contamination here. And that's because the component that is getting ready to come off of there, if that component has a very high boiling point, then that component has a chance to condensate back in the interface and turn back into a liquid and never leave, unless we heat that interface up to a hot temperature in order to get it out. So this is the problem that we are going to see in the gas chromatography world. And the issue is that temperatures, which really directly relate to boiling points, will play a very important role. So we have chosen compounds for this lab experiment that is below 250 degrees for their boiling point. And the reason for that is because if we chose anything higher, it could kind of crap up in the interface and it could begin contamination problems for us, and we don't want that to happen. All right. So that was set. You can go back and take a look at what temperature that was set at, but that was set at a certain temperature for that reason. So I had to kind of know a little bit about what I was injecting before I actually injected it onto the machine and had the settings to kind of get the machine to do what I want it to do. All right, up next, another temperature setting that you saw on there was this ion source temperature. So that is the piece that's going to be in the mass spec system right here. So after the interface, it typically goes into the ionization source chamber, and that is where it gets punched, and that's where it loses a tooth, and that's where it begins to fragment up. All right, so in that area, there's kind of an ion source that's an electron beam, and this is typically in a housing, and this housing is also heated. And we need that heated because, again, we do not want those to turn into a liquid in the mass spec chamber and kind of contaminate and sit there and cause us problems later on down the future. So this area is heated, kind of like the oven in your kitchen. It's just
just a closed environment. The samples will make their way into the ionization source, and then the sample will hit the ionization beam, and that's where punch happens, and then that's where we get this kind of fragment molecule with these charges, these positive and negative charges, and then one will make its way down the MS and the others will be sucked out of the MS. And I'll let you go back and watch the lecture videos to figure out which one is which. All right. So that is also a temperature setting that we need to make sure that we double check. So if our compounds have a higher boiling point than the heated ionization chamber, then there could be an issue with contamination later down the road. All right. The other two things were the M to Z ratio. And the M to Z ratio was at the bottom of that computer screen. And you saw that we set it at 35 and the maximum was like 200 and some. So the question that I always get, I'm just going to say 250. It might not have been 250. I can't remember, even though I played it just 1 or 2 minutes ago. But 35 and the maximum, why do we choose these? They just seem like random numbers. And, what does that actually mean? Well, in the M to Z fragmentation pattern, what we're saying is that anything below 35, we don't want you to kind of report on. We don't want you to see. We don't want anything like that at all coming through or getting detected. And there's a reason that we choose 35, and that's because we are assuming that all of these are under very high pressure and that this is in a sealed vacuum environment, all right? But every now and then we could get leaks, and that leak could come from something like air. Air from the room could make its way into that machine, and then all of a sudden we're going to start seeing air peaks that show up, and this is going to be part of the mass spectrum, and it's going to cause me problems. So what we do, the trick that we begin to kind of play here, is that the lower M to Z value range, that 35 mark, is set in particular for one reason. The components of air, what are they? Well, you might think O2, oxygen gas, because that's what we breathe. Okay, well, good for you. O2. Well, the formula weight for O2, well, oxygen 16 and another oxygen 16 and 16 and 16. Oh, 32. So it's right below the 35 minimum. Again, anything below 35, the machine is going to ignore. So if we do get some kind of weird, strange signal from oxygen gas that's made its way in, then our values and the data is not going to be tampered with. We don't have to worry about that, quote, contaminant that comes through. Something else that's in, that just in normal air, this is not the major component, by the way, nitrogen gas. Nitrogen gas, that's 14 and 14, so that's 28. And then you might say, well, what about CO2, right? That's carbon dioxide. That looks like 32 and 12. That would be over. Well, that's true. And that also means that I could take my breath and I could blow it into the instrument, and the instrument would recognize that as a component that has came through the machine, and it will recognize it and it will do a measurement for it. Think about that. It's a very high-tech, sophisticated way to figure out if you've got bad breath. So these are the settings that's on the instrumentation software that you saw just now. All right. So now what I want to do is look at the software again. This sample is actually running at this moment, and you'll get to see the generation of a real-time chromatogram as well as mass spectrum that gets generated from the machine. All right, folks, so this is our mass spec screen, or our software screen. And what you're seeing here actually is a peak that was just registered with our instrument. So what happens is that in the beginning of the injection, I see nothing, the software sees nothing, the mass spec sees nothing, and we go pretty close to what we would call the baseline. All right, so I'm going to give this a little bit to kind of come into focus. There we go. So this baseline is just all flat. That's what we like to see, so nothing's coming through, and then all of a sudden, ding ding,
we have a compound that shows up, and that compound, whoop, all the way up and whoop, all the way back down. So this is a sign that the mass spec has seen something. What it has seen, I don't really know yet, because this is just a visual of the chromatogram as it's getting generated. But look at this. Da-da-da-da. We see something else that's showing up. So I told you very often these compounds are not pure. They have impurities that are with them. These impurities can be 1 to 5% depending on what we order and what we need and how expensive it is. But this mass spec system has now separated two components from each other, and these two components that you're seeing here, we have no clue what they are yet. The mass spec will tell me that, but looking at what we call the chromatogram, which is just the signal from the machine, I really have no clue. So now what you see here on the bottom is it's going back down to baseline. It will stay at the baseline as long as it's not seeing anything to come through. And then if it does see another impurity, and maybe it will, maybe it won't, but if it does see another impurity, I'll see another pew, up it goes, and down back it goes. On the computer screen, this here at the bottom is the mass spec. So this is what we would call the chromatogram, which is where all the separation takes place. It gives me an idea of what's in my sample. And then down here will eventually be the mass spec screen that I will begin looking at, that I will begin analyzing the mass spectra, and that I will be kind of doing a database search with. All right, so that's a little bit of the view that I'm seeing as a user for a mass spectrometer system in today's analytical laboratory type of environment. All right, so I'll go into more detail about certain areas of the software, but folks, once again, a general overview. This is what we call the chromatogram, which is the identification of all of the sample and its impurities. And then here at the bottom will be eventually the mass spec that we'll take a look at in just a second.
All right, so a little bit of intro about the software, the GC portion, the MS portion. Again, we're only focused on the MS portion, and that is it. But it gives you kind of a general overview of the mystery that happens behind the injection and how we obtain the MS. A lot of people ask us, well, what does the program actually use the MS for? We actually use it for a number of things, folks. The mass spec is heavily used in our laboratory. We can actually use it for any type of pharmaceutical use. So if we're producing some type of tablet or medication and we want to look at maybe that particular active ingredient, or maybe the contaminants that could be coming along with the tablet or that liquid solution or whatever we're making, we can analyze that on a mass spec, and it would kind of tell us what is present and what is not. Environmental does a great job with mass spec, and these are things like pesticides and herbicides. So if I'm out in a field and I'm spraying crops down with some type of pesticide, and I'm afraid that that pesticide has gotten onto the surface of my apple, and then I need to bring the apple into the lab and I need to kind of wash it off and extract the pesticide to see if it's made its way onto the skin, then we can do that in our laboratory, and the mass spec will not only tell me that it's present, but it will tell me what types, plural, what types of pesticides have been used that's still on the surface of that object or that fruit or that vegetable or whatever the case is. That also kind of goes hand in hand with the food industry world, because very often some people are very focused on this term organic, and organic makes me sound like I'm eating all healthy and all natural, and I'm spending 5 times the amount of money for an organic type of product at Whole Foods. Well, how do you know it's actually organic? How do you know there's no pesticides or herbicides or anything that they have put onto that food product before they sold it to you? Do you have one of these at home? Of course you probably don't. So some of this has to go through testing, and these are very easy ways that we can detect any of the presences of these pesticides and herbicides in the environmental or food industry. I'm talking about pesticides and herbicides, but pharma world and environmental world actually go together to look at water discharge. So if we have a water company that's pumping out water because they have used it already, they've kind of done some cleanup and they're pumping it right back down into the Cape Fear River. Keep that in mind the next time you drink tap water. They are pulling your water from a live stream or river like the Cape Fear River, and they are putting it in-house to clean it up. They send it through your tap. You use it for whatever you use it for. Then it circulates back to the water company, and they discharge it back into the Cape Fear River. So the further you are downriver, the more and more that you are exposed to everybody's trash that lives up above you. So the water wastewater world also is using mass spectroscopy as well, and that's because they are now finding things like cocaine in the water supply. These common drugs like Viagra, that's one of the most common drugs that we find in water and wastewater. So, depending on the day, just go over to your tap, fill that glass full of water that you're going to get ready to scoff down, and it could be cocaine Viagra tainted water, and you would never know that. But they're there. They're very hard to get rid of. So mass spec has that power. Forensics and clinical laboratories actually would have a use for mass spec as well. And on the forensics and the clinical side, again, we're looking at typically here for this particular MS runs, illicit drugs mainly. So, methamphetamine, cocaine, heroin, a lot of these drugs we can just kind of shoot onto an NS and figure out if they're present, and then figure out the concentration of them, either in spit or blood plasma or saliva, or that's spit, but of urine. So those are other options that we can do with an MS that have some applicability to them. And of course, the clinical side of the house would be looking at very similar things as well. What kind of drugs are you taking? What kind of prescription medication do you have? Is it still present in your blood system? Is it found in your plasma? Is it found in whole blood? Is it in your urine? Are you metabolizing it the way that you're supposed to be? All of this is all forensics and clinical driven as well. So just some kind of concepts about why someone would use a mass spectrometer, and why we kind of go on and on and on and on about this. All right. So now that this one sample has been finished, we're going to take a look at the software in the post-run section, and we want to take a look at the mass spec. How do we get the mass spec of the compound that was just analyzed? So sit back, enjoy the show. In a couple of minutes, I'll talk to you again.
All right, folks, so I want to show you what I'm doing on the software as far as the MS is concerned. So this is after a sample has been analyzed, and what I'm seeing on the screen here in kind of the beigey cream area is, again, something that we call the chromatogram. So what I'm looking for is at the baseline area, which is pretty close to 0, or it should be. I shouldn't really see any deviation from that baseline at all, right? Now, that line that you're seeing there, that actually means nothing. It's just where my cursor is going to go. So ignore that black line that's there. But I really don't see any type of signal at all. Maybe a little bloop right there, but nothing major. And then as I go through, these are in terms of minutes. So at 7 minutes, it still sees nothing. 7.5 minutes, it doesn't see anything. 8 minutes, it doesn't see anything. And then right before 8.5 minutes, whoop, and then all the way back down. That is a sign that the mass spectrometer has seen something. So something has come into the ionization chamber at this point. It took around 8.5 minutes for it to make it there, but the mass spec did see something, and it knocked out a tooth. So we need to figure out what type of compound this actually is. So there's a very quick, easy way that I can do this. So if I back up on the computer software for just a little bit, you can see my mouse. There's the cursor. I'm going to come over here to this peak, is what we call that, and I'm going to double click that peak. And now when I do, I want you to take a look at this bottom area that's more of a whitish type of background. This is my mass spectroscopy, or my mass spectrum down here. So I'm going to double click the peak, double click, there we go. And if you noticed, these lines down here now have changed. That is the mass spectrum that's assigned to that peak that I have double clicked. So notice what happens if I go out here somewhere and I double click here. My MS has now changed down here at the bottom. It no longer looks the same. So I'm getting the mass spectrum of whatever compound is coming through, even if there's not just maybe just helium or air coming through. I'm still getting that mass spectrum along the course of the chromatogram. But this is the thing that I'm interested in right there. All right, so we're going to double click that peak again, and when I do, the mass spec changes down here at the bottom. Now if I zoom in on the mass spectrum, you're going to see that typical M to Z ratio that's down here at the bottom. So this is 40, 50, 60, 70 M to Z. And then you also see the lines, or you're starting to see a generation of the fragmentation pattern that's happening down here. So I see a pretty tall line here at 77. I see one there at 51. I don't really see anything there at 62, but the software picked it up and it listed it. Here I see something like at 78, and as I scan this M to Z baseline here, I also see a 156 that's pretty tall, and then nothing really after that, and then an M plus 2 peak that's about the same height that's right there. So it looks like this M plus 2 peak is about the same intensity as the M peak. So that will give me an idea of maybe, possibly, what type of compound this is. All right, so I'm going to go another step further though. I'm going to right click on this screen, and when I do, you're going to see an option here that says similarity search. Now this is something that you cannot do on your end. And that's because it will cheat and it will give you the answers. But I want to show you the power of the MS system. All right, so if I click the similarity search, now what will happen is a computer screen will show up. That's what we call the database. And this database is basically looking at my mass spectrum, which is right here on the computer screen. That is what my sample obtained. And it quickly, in a matter of like fractions of a second, match that to a database mass spectrum that we have in-house. So here, and we've paid thousands of dollars for this database system, by the way, folks. So here is the mass spectrum that it thinks that matches up pretty well. And what this is going to do is over here to the side, it gives me the molecular structure of that compound. So it looks like this thing is bromobenzene, and folks, sure enough it is. So the power of the software system is very good, but it's only good because bromobenzene has a particular mass fragmentation pattern that only bromobenzene has, and that is it. So this is my original, and this is the database reference to what matches the best. Up here at the top, you're also going to see a table that shows up, and this table will list all of the possible compounds that this thing could be. It's not just going to tell me one and one only. It's going to give me an assortment of things that maybe it feels pretty good about. It will rank them over here at the side. 100 is going to be the best possible scenario. It's like a perfect answer or a perfect match. But this very first one is a 98% confident that this thing is going to be bromobenzene. Notice the dollar bills. Dollar bill, y'all. Okay, that dollar bill is going to separate names. So we have a name separation here, and this thing is also called bromobenzene, and we have another name separation there. And actually, if I grab that divider and just kind of drag it out, it's going to say this could also be called monobromobenzene, dollar bill. It could also be called phenyl bromide, dollar bill. It could also be called 1-bromobenzene, dollar bill, and it gives me kind of this code that the molecule could be known as. So this is a way to say, listen, there's more than one name for a compound. I know that we mostly call it bromobenzene, and that's what's showing up here on the front end. However, there's also other names, plenty of them, that this thing could be known as. And if I just drag out that table, it's going to tell me what all of these other names might be. And it does that by separating with the dollar bills in the Shimatsu software. All right, and that's probably because it took a lot of dollar bills in order to purchase the software, and it took a lot of dollar bills to purchase the machine as well. All right, so that's the power of the instrument, but this is something that you will not get to experience because let's face it, your job is to analyze the MS, figure out the fragmentation pattern and try to match the fragmentation pattern to a molecule of choices, right? So that's what this is all about. If I go into the report setting and I pull up the report, this is probably what it's going to look like for you. So on the report that I will print out, scan, and send your way, you'll see the chromatogram up here at the top. Again, one component only. And then the mass spectrum is going to be down here. So this is the mass spectrum of the main component that I will provide. So the mass spectrum will have all of the lines, the fragmentation pattern that you'll see here, but it will also provide you details down below. And this is a mass table, and you will see two columns. One is going to be an M to Z, which is the formula weight, and one is called the relative intensity. So that is how tall the actual line is. So the relative intensity here of 100 would be in reference to the tallest peak, and the tallest peak is always the base peak. So it looks like this base peak is around 77, and then in this table, if I find 77, that relative intensity will be 100 for you. All right, so that's what those values are going to mean down below. This will give you a table of numbers. A lot of them will say zeros, which means it didn't find really anything there at all, but it will give you a table of values of M to Z and the intensities of those peaks, so you can make a judgment call on if those peaks are important or not. All right? All right, so that's a little bit about the software. I'll keep running these samples one after another, and I'll provide all of these reports to you, scan them, send them your way, so that way you'll have.
Okay, so now you know a little bit more about the basics of running a sample, getting it onto an MS instrument, and kind of connecting real life to what is often shown in a textbook. So this is what your reports are going to look like. I want to take just a minute or two and talk about the actual report and where to find this information, so that way it will help you out when you get ready for this. So up at the top, you will see the unknown number, and the unknown number will be in the sample name, and that's right up here at the very top. So it says GCMS intro UNK unknown 1. So you're going to have an unknown 1, an unknown 2, a 3, a 4, a 5, a 6, 7, 8, and 9. Who knows? There are probably anywhere between 11 to 14 unknowns. You'll know that by taking a look at the data reports and the data sheet when you print that off or when you start working on that. So that's where you'll find the unknown letter. All right. This top portion here, this is really nothing that you need to know anything about. It's just the chromatogram. That is the presence of a compound that has came through. And then I've double clicked that peak in order to generate a mass spectra that sits down below the chromatogram. All right. So the spectrum is going to follow the chromatogram, and that's what these things are going to look like. I'm sorry that they come off very fainty like this. You know, it could be a little bit hard to see, but that particular day when the printer was printing, it just wasn't very, very dark. It needed a new inkjet printer. But I think that it's doable. I think that you'll be able to view these without a problem. So the first thing that I'm going to do is take a look at this mass spectrum, and then I'll come down here and, you know, folks, it gives me some information that I don't want to take advantage of, or that I want to take advantage of, right? I don't want to ignore it. And one of the things, look, it says base peak 93. So it actually tells me what the base peak is, and the base peak is really the tallest peak. And the tallest peak on this particular compound is 93. That's right there it is. And that's what the software told me it was. So it's telling me that the base peak is 93. It's showing me that the tallest peak is 93. And then in the data fragmentation table, if I look at 93, which is going to be right here, I see a 100 that is assigned. And that 100 means the tallest. That is how the software reports the height or the intensity of these fragments. So 100 is the highest it can go, 100 is the tallest that it will go, and 100 in the fragmentation table means that 93 is the tallest peak, and on the graph it tells me that it's the tallest peak, and then right below that it tells me the base peak was 93. So very, very important. I'll need to know that when I'll work through these match game problems. All right. The next thing is the M peak. Now, keep in mind the M peak is the formula weight of the compound. And it is okay, like we've talked about in the lecture videos, for the M peak to be the base peak. Sometimes that just happens, and that means that the molecule does not prefer to fragment. When it goes into the ionization source, it prefers to stay together, and it's really hard to punch it. It's really hard to knock out a tooth. Maybe it doesn't have any teeth to begin with. It's just running on dentures. But this compound has made its way to the detector fully intact. So this is something that we want to keep in mind. M peaks can be base peaks. Not every time, not all the time, not often even, but it can happen. All right. And then I'm probably going to, in the data sheet, will say, take a look at the M to Z fragment of 66 for unknown compound 1. All right. So you'll come to this and go, oh, look, there's 66. That's a pretty common fragment. I see it's a really tall line. So the question here is, what fragment will give you 66, and we want to draw the structure of that fragment that will deliver that to us. All right, so the M peak is just going to be formula weight. The base peak will say, what is the base peak? And you write it down. You better not miss it because it's all over the place on each one of these reports. That should be a very easy point earner for you. And then it will ask you to draw the fragment that gave you the base peak. If it stays together, it stays together. But if it breaks up, draw the fragment that made that base peak happen. And then there's going to be maybe one, possibly two, right, of these other fragments that show up on the MS. And I will pick them. And I will tell you, focus on this M to Z. And I want to know what fragment made that 66 happen, or what fragment made the 39 happen, or what fragment made the 46 happen, or what fragment made the 78 happen. I will tell you which ones I want you to determine, and that will all be on the data sheet when you upload that and when you begin to work on it. All right, so that is what the MSs are going to look like. Again, chromatogram up at the top, the spectrum follows below. It tells you what the base peak is with almost every single one of them. And then take a look at the table if you need it. And the reason that you might need to look at the fragmentation table is to maybe determine the formula weight peak. Right? So if you look, we had this thing go all the way to 250. There it is. It goes all the way to 250. But you're seeing a lot of zeros here. Look at that. 0, 0, 0, 0, 0, 0, 0, 0, 0, all the way down. 0, 0, 0. Oh, we get like a 0.01, but that's okay. You might as well say that's kind of like 0.2. A lot of these are just super, super tiny. There's no signals at all involved. But we start getting signals like, look at this one, 94.1, a 9.6 or 6.96 relative intensity. We have a 92, which is an 11.58 relative intensity. That means those lines are pretty tall. All right, those lines are there. They're not zeros. It's not just a little glip or glitch in the software. They're there. And if I look at 94 and 92, well, here's 93. Look, right there's 94, and there is 92. So in those lecture videos, you probably have an understanding now of why we see these small little signals that go and flank the left hand and the right hand side of the major fragment table or the major fragment weight. So just keep that in mind. They are there, and that's possibly why you would need to use the fragmentation table to help you determine what a formula weight might be of the compound. All right. Okay, so there you go. There's kind of the information that you would need for this particular lab. Again, it's all match game, figuring out what fragments are creating which formula weights that show up on the spectrum, and then figuring out what unknown number 1 is, and unknown number 2, and unknown number 3, and so forth. So again, if that was you and I kind of tackled this, I would do formula weights first. And then I would go through and take a look at these formula weights that show up on the MSs. Look, that one was like 156. And look at this one. This one's like a 108. So that will give you a better kind of narrow field of which unknown goes to which sample. Use the formula weight of a compound first, and then worry about the fragmentation pattern a little bit later. Here's the spectrum from unknown number 4. Notice super tiny, no peaks really at all here. I see like the first major one here at 70. So do I have a compound with a formula weight that's close to 70? If it's way over 70, I'm going to cross those out. Those can't be a choice, right? If I've got a formula weight of 100, then that can't be a choice for this one. So I know I can just automatically eliminate it and kind of narrow down my selection to figure out which one's which, okay? All right, so good luck on the match game. Use formula weight to identify the unknowns. That's probably going to be your best bet. And then use the fragmentation pattern in order to figure out kind of what formula weights match to what fragment. And you'll have to draw those structures and upload that data sheet. All right, so good luck on your mass spec journey. I'm here if you need any questions. I'll be glad to help. If you can do the infrared, you'll find this is very similar to the infrared. It's just in the mass spec world and not in the infrared world. All right, so good luck with the lab experiment. If you've got questions, let me know. Keep in mind, sometimes these things do funny things. And if you can get a fragment that's like 1 hydrogen off, then that's a pretty good sign that you're picking the right fragment. But not everything happens textbook. Not everything happens perfect. So if I can figure out a fragment that will give me 54 and not 55, I'm pretty close to where I need to be, unless something weird and strange is going on. So don't freak out about that. Don't think that you have to have a perfect number, because your number will be close. That's all that matters. All right? So good luck. If you got questions, again, you know how to contact me. Until next time.